Welcome to This Explainer. Today, we're taking a seriously fascinating journey, one that bridges the gap between the everyday language we use to talk about our day-to-day lives and the absolute mind-bending physics of the multiverse. We're going to explore the actual mechanics of time itself. We'll break down how we think about it, how we might actually travel through it one day, and crucially, what happens to reality itself when we do. So think about this. If you change the past, does the future still exist? I mean, it sounds completely like science fiction, doesn't it? But this single, highly provocative question has literally kept physicists, philosophers, and logicians awake at night for decades. And to really answer it, we have to unravel some of the most profound paradoxes ever conceived by human minds. Okay, let's dive into this. Here is our roadmap for today. We're starting with number 1, the language of time. Then 2, fast forward, the future. 3, rewind, traveling to the past. 4, paradoxes and causal loops. And finally, 5, saving the universe. We are building from basic grammar all the way up to the fate of reality itself. Part 1, the language of time. How we structure time before we travel through it. Now, what's really interesting about this slide is that before we can even think about building physical time machines, we really have to understand how our brains already unconsciously encode time. The study of time isn't just for quantum physicists, it's actually a massive focus for linguists too. Research like this really comprehensive exploration from the National University of Uzbekistan looks at how entirely different languages use tense, aspect, and mood to encode temporal information. Across different cultures and cognitive frameworks, the language we speak actually shapes our conceptualization of temporality. To put a precise term on it, we use something called temporal deixis. This is basically the use of words or grammar to anchor an event relative to our present moment. I'm talking about words like yesterday, now, or tomorrow. So in a very real sense, our everyday language acts as our first, totally invisible time machine. It seamlessly orients us between past, present, and future orientations long before we ever start looking at blueprints for a flux capacitor. Which brings us to part 2. Fast forward. The future. Forward-directed time travel is theoretically inevitable. Right. This is where we shift gears from cognitive linguistics to applied physics. You might be a little surprised to learn that among scientific experts, traveling to the far future isn't just a fun fantasy, it's highly likely. Scholar Charles Tandy outlines practical future-directed time machines, and he argues that this capability is what we call overdetermined. Basically, that means it's pretty much guaranteed by multiple converging technologies. These fall into 2 main categories: biostasis, which ranges from experimental all the way to perfected long-term suspended animation, and super-fast rocketry, which utilizes near-light-speed travel for astronauts or even entire extraterrestrial communities. So we essentially have 2 paths to the future: the biological approach and the physics approach. With suspended animation, or cryogenics, you're essentially just pausing the biological clock. But with super-fast rocketry, you're exploiting Albert Einstein's relativity. It's the famous twins paradox, which, by the way, physicists now consider scientific fact. Imagine an astronaut traveling near the speed of light. They might experience what feels like a 6-week vacation, but then they return to Earth to find that 6 centuries have passed. Both of these methods absolutely transport you to a future timeline. Moving on to part 3, rewind, traveling to the past, the hard question of backward time travel. Going forward is, relatively speaking, pretty easy. It just requires enough technological advancement. Traveling backward, however, that is intensely complex, highly debated, and fundamentally challenges our entire understanding of reality. So the crucial point is that we must distinguish between 2 types of past-directed interaction. First, there's simple time viewing, which is passively observing the past without any possibility of interacting with it. And then there's complex time travel, where a human actually interacts with the past in a way that could alter the timeline. One is basically a safe historical security camera. The other, well, that's a recipe for absolute cosmic disaster. And that brings us to part 4, paradoxes and causal loops. When breaking the past breaks the universe. Think about it. If you can actually change the past, logic itself just begins to unravel. The most famous example of this is the consistency paradox, which you probably know as the grandfather paradox. In modal logic, if the past happened in a certain way, it's a fixed, necessary truth. So, if a time traveler goes back and changes an event, say, accidentally preventing their own grandparents from meeting, they essentially prevent their own birth. But if they were never born, they couldn't travel back in time to change the event in the first place. It creates an impossible contradiction that completely breaks causality. And this brilliantly illustrates the concept using physics instead of people. Physicist Joseph Polchinski devised a kinetic motif called the billiard ball thought experiment. Imagine a billiard ball fired into a wormhole. It exits in the past at the exact angle needed to strike its younger self. That strike knocks the younger ball off course, meaning it never actually enters the wormhole in the first place. So, what hit it? There's no answer. The logic just entirely collapses. Then we have the bootstrap paradox. Physicists Andrei Losov and Igor Novikov beautifully named this after the jinn. Inspired by the entity from the Quran that leaves no trace, a jinni in physics is an object or piece of information that simply loops in time. Imagine traveling to the past and giving a young William Shakespeare a copy of his complete works, which he then simply copies and publishes. Who actually wrote Hamlet? The information just exists, possessing absolutely no true origin or creator. Mind-bending, right? Let's move to and see how this builds into our final section, Part 5. Saving the Universe, How Physics Attempts to Fix a Broken Timeline. Because physicists really don't like broken logic, they've had to develop frameworks to rescue reality from these timeline-destroying paradoxes. There are two leading resolutions here. The first is the Novikov self-consistency principle. This dictates that the timeline is fixed. The universe simply will not allow a paradox to occur. If you try to stop an event in the past, your actions will actually end up being the very thing that causes that event. The other resolution is the interacting many worlds theory. In this quantum multiverse model, if you change the past, you aren't overwriting your own history. You branch off and spawn an entirely new parallel universe. Which leaves us with a pretty profound final thought. If the Novikov principle is true, and the universe forces consistency to prevent paradoxes, doesn't that mean time travelers have no free will? Well, as physicist J. Craig Wheeler points out, physics already restricts your free will every day. You may will yourself to fly or walk through a concrete wall, but gravity and condensed matter physics dictate that you cannot. Why is the consistency restriction placed on a time traveler any different? It really makes you wonder, doesn't it? Is our entire sense of free will just an illusion inside a mathematically consistent loop? Think about that the next time you find yourself wishing you could rewind and change the past. Thank you so much for joining me on this explainer, and keep questioning the universe.